Yeah, so this is going to be a series of lectures connected to some of the other lectures you've seen. But it will take things in kind of a different tack. Like I'm going to try to survey a lot of different topics, different results that have been proved, sort of stalking lower bounds and algorithms in a sense. I'll start with the algorithm side, so that's what this lecture is about, because it seems like that's the part we understand best, algorithms. Okay. So I'd like to start with a conventional view of algorithms and complexity, as I have seen it and was taught. So I was taught there are two kinds of people. There are algorithm designers, and there are complexity theorists. And the algorithm designers ask, positive things, what makes some problems easy to solve, when can I find an efficient algorithm? And the complexity theorists ask negative things, what makes other problems difficult? When can we prove the problem isn't easy? When can we prove a lower bound, the resources needed to solve a problem? So, stated that way, the tasks of the algorithm designer and the complexity theorists appear to be inherently opposite. One is trying to find an algorithm, one is trying to rule it out. And furthermore, it's generally believed that lower bounds are harder than algorithm design. And the intuition there is pretty strong. In algorithm design, we only have to find a single nice algorithm that solves the problem well, okay, for whatever notion of well we might come up with. Whereas in lower bounds, we somehow have to reason about all possible algorithms and argue that none of them work well. Okay. Somehow we have to reason about algorithms we will never even see and argue that none of them will work well. Well, Russell sort of hinted at the kind of false difference between these two, that my intuition about these things. So in worst case algorithm design, for example, yes, we only have to find a single algorithm that works well, but it needs to work on all possible inputs, including ones we will never see. Okay? And so this is, and miraculously we can do this, okay, for like many problems. So maybe we should not be so intimidated about reasoning about all possible algorithms, provided we set things up in the right way. And so a lot of these lectures are going to try to think about how do we set things up in the right way so we can reason algorithmically about lower bounds. Okay. So this belief is strongly reflected in the literature. Just look at the relative sizes of SOTA and CCC, and that's sort of the high order bit of like algorithms, hundreds of algorithms papers each year, and very few lower bounds papers, including in CCC. Okay. All right. So what I want to promote in these lectures, and what other lecturers are doing, is promoting what I call a duality between circuit analysis algorithms, or as Russell calls them, meta algorithms, and circuit lower bounds. Now, I put duality in quotes because it's not entirely formal. Sometimes you can make it formal what you mean. Other times, we only have connections in one direction, or we kind of have intuitions, like we can match up quantifiers, like we can match up the quantifier of the circuit and quantifier of the input. But in general, the thesis is that in many cases, algorithm design can be as hard as proving lower bounds, okay, which is counter to this conventional view. The idea that designing a single algorithm for solving the right kind of problem would actually just yield a lower bound for you. Okay. So, in fact, there are deep connections between the two. Russell will talk about the de-randomization connection, mostly. But they're so deep that often they're the same. Sometimes you can set up equivalences, but as mentioned before, the equivalences are not so nice. Like sometimes you need various technical conditions to get an actual equivalence. Okay? But the kind of connection I want to talk about, sort of the most kind of counterintuitive connection where the design of an algorithm can lead to a lower bound. Okay? So like a typical theorem from algorithm design says, here's an algorithm A that solves my problem, all possible instances of the problem. And a typical theorem from lower bound said, here's a proof P that my problem cannot be solved on all possible algorithms from some class. Okay? What I want to do is somehow draw an analogy between the algorithm being designed, the algorithm A being designed, and the proof of the problem can't be solved. Okay? An analogy between all possible instances of the problem. In our case, it will be like a fixed computational object, like a circuit. And an analogy between that and all possible algorithms from some class. So this will be all possible circuits from some class. Okay? Okay? So, so more precisely, okay, what I want to do is set the following kind of quantifier match. So suppose I have a Turing machine, okay, and there exists a Turing machine, and it's computing some non-trivial circuit analysis problem. Okay, it's solving some problem. Like, for example, on all possible circuits, this is supposed to be a circuit, from some class, maybe formula-like, it will report whether it's satisfiable or not, for example. That would be some non-trivial circuit analysis. Be just checking whether this circuit computes a trivial function or not, a function which is all zeros or not. Okay? Okay, so suppose there exists such an algorithm that does this for all circuits. I want to take that kind of statement and say there exists a function f based on the algorithm I designed, say, such that for all possible circuits, this circuit cannot compute this function. Okay, in a very precise sense. So we will get circuit lower bounds. Okay? As also was sort of talking about, it's sort of like a game that when the algorithm succeeding in analyzing the circuit, sort of tantamount to the circuit failing to compute the function. Okay. So we'll have some connections of this form here. But at least at a high level, I hope at least the kind of quantifier match I want to do is clear. Okay. These are super high level. Okay. All right. Okay, so the outline of these lectures will be as follows. So in this lecture, I'll talk about circuit analysis algorithms, or meta-algorithms. And then over the next two lectures, I'll talk about circuit complexity, just reviewing basics in circuit complexity, what's known, what isn't known, connections between these two topics, circuit analysis algorithms and circuit complexity. When can complexity imply algorithms? When can algorithms imply lower bounds? And the last lecture, I'll give the proof of a particular lower bound, that non-deterministic exponential time doesn't have small circuits from a particular class. Okay. Called ACC. Okay. Alternating circuits with counting. Okay. The main thing to think about right now is, whatever those acronyms mean, is that this sort of question seemed out of reach until a few years ago, and really all that was needed to prove such a result was just to look at what the lower bound problem required in the right way. Okay, so that's sort of what I want to emphasize, and to talk about different ways of looking at what is required, okay, to get a lower bound. Okay, so on to circuit analysis. So circuit analysis problems, in general, they're computational problems so sometimes they're on circuits given as input. Okay, sometimes they're on truth tables of functions. We'll focus mostly in this lecture on problems where the circuit is given as input. So your input is a description of some logical circuit, let's say over AND and OR, not gates of fan into. Generally speaking, the particular circuit basis won't matter. I will tell you exactly when it does. Okay. So that's the kind of input, and the output is some property of the function computed by this circuit. Okay. So this circuit is taking some number of inputs and outputting, say, a single bit, and I want to know some property of the truth table, the string of that function. Okay. So the canonical example of this is the circuit satisfiability problem, circuit SAT, where your input is a logical circuit C, and you want to decide, is this function is this basically the function computed by this the all zeros function, okay? Or does it have an assignment that makes the circuit print 1? Okay. Of course, as we know, it's NP complete, but we can still ask if there are algorithms that solve circuit SAT that are faster than the obvious brute force algorithm, the algorithm which would try all 2 to the n input settings to the n inputs of the circuit and just stick it in and evaluate the circuit through. We can still ask if there are any algorithms solving this problem faster than that. Okay, we don't because of incompleteness, we don't think it can be solved in time. Polynomial in n and the size of the circuit. But maybe there's something faster. Okay? Mohan talked about SAT for the K-SAT problem. We're going to be talking about that more broadly here. Okay, so we'll talk about a generic circuit satisfiability problem. So like let fancy C be a class of Boolean circuits. So C could be Boolean formulas, so circuits that look like trees when you write them out as a DAG. They could be just arbitrary circuits. They could be CNF formulas. They could be K-CNF formulas, in which case we'd have the K-SAT problem. In general, we'll have a CSAT problem, which says, given a circuit K from that class, is there an assignment to the inputs, the n inputs of the circuit, that makes it print 1? Okay? So you could have, K-SAT, which is for K-CNF, formula SAT, which is for formulas, and so on. Okay? Again, this problem is NP-complete for essentially all interesting classes C, and it's solvable, obviously, using brute force search. Try all possible assignments, evaluate them in time roughly linear in the size of the circuit. Okay? And we want to know to what extent this can be beaten. And later we'll look at when this can be beaten, what can you say about the circuit class C? Okay? So, there are two reasons to think about solving this thing faster. One is just purely intellectual. We have an obvious, silly algorithm for solving the problem. Can you do something better? Can you avoid being silly? Okay, even in the worst case. That's one motivation, and that motivated lots of people. Okay, people working on this long before I was thinking about it. But the new motivation, another motivation, alternative one, is that solve things like CSAT faster, and you get insight into what the class fancy C can compute. Okay. You can prove limitations on what the circuit class can compute based on how well you can solve the CSAT problem. Okay. All right. Okay. So circuit SAT algorithms. So for simple enough circuits like K-CNFs, as Mohan discussed, we know of algorithms faster than 2 to the n. Okay. So for example, 3-SAT, one mentioned is in 1.308 to the n. Okay, that's randomized. So you can think of this, right? You can think of a 3-SAT instance as a big AND gate of ORs with fan in 3, and these wires here point to variables or their negations. Right? This is sort of rewriting what K-CNF or 3-CNF means here. Okay, for 4-SAT, you can't get 1.3 to the n, as far as we know, but you can get something slightly faster. And for K-SAT, as Mohan showed, you can get algorithms that run about 2 to the n minus n over order k. Okay? So this is by many, many, many authors, and the 3-SAT is from Hurley recently. And so the main observation I want to talk about here is that all known faster than 2 to the n time algorithms for K-SAT have the property that as k goes to infinity, this constant c in the base of the exponent goes to 2. Okay? In fact, it seems you get this kind of behavior no matter what algorithmic paradigm you use. And that is actually, to me, a very intriguing phenomenon. Like even getting like a log k there, we don't know how to do. Okay, so this led to the following hypotheses. The strong ETH, which says that for all delta less than 1, so like think of delta as like 0.999, there exists some constant k, so that K-SAT requires 2 to the 0.999 in time. Okay, so essentially, getting any string of 9s is just not possible. There is some constant k for which the clause width will be so large you cannot even get that string of 9s to the n time. Okay, so what it is saying is that you just can't improve over this base of the exponent 2 as k goes to infinity. So Virginia talked about this, and Mohan talked about this, so I won't talk much more about it. Okay. And there's also the ETH, a weaker thing, which just says, solving 3-SAT requires 2 to the delta n time for some delta greater than 0. Okay, so there's 20, 30 odd years of work here, and you're just never going to have some infinite sequence of exponents getting closer and closer to 1. Okay, there's some constant out there, maybe 1.1 to the n. You're just never going to solve 3-SAT better than that. That's ETH. Okay, and strong ETH does imply ETH. Okay, so far I haven't heard arguments in these lectures, compelling arguments for strong ETH. But here's here's what I would consider to be the most compelling argument for strong ETH, because people have heard me complain that I think strong ETH is false. So let me play devil's advocate, just to confuse you. Okay, so the main thing is that this exponent is really remarkable. This kind of behavior, like the best analyses of backtracking algorithms we know, they get essentially this behavior with a certain constant here. The best analyses of local search that we know get the same rough behavior, maybe a different constant here. Okay. There are dynamic programming algorithms which you would never run in practice, right? Backtracking and local search, they at least have polynomial space. Dynamic programming things will take exponential space. You can do all kinds of crossing. You still get that. Timothy Chan and I recently threw a lot of complexity theory tools at trying to solve orthogonal vectors and KSAT faster deterministically. We have a new algorithm which can actually count satisfying assignments to KSAT. It's very radically different from any of these things. Still has this behavior, counting, but at least we can count assignments. So there's something about just getting beyond this kind of behavior, which seems interesting. Like the fact that it's shared by backtracking, which is a totally different class of algorithms, from local search, a totally different class of dynamic programming. The stuff we use is like algebraic in nature. All of them get you this kind of thing when you optimize everything. So that's sort of the best reason I would think of. But like that actually says this is the right answer. That says something stronger than strong ETH. So that'd be super strong ETH. Okay, you can quote me on that. Okay, in this video, that's a super strong ETH. Let's prove it false. Okay, all right. Okay, so enough about that. So now I'm going to differ a bit from what Mohan was talking about and talk about more expressive circuit classes than just K, C, and F. So you can think of K, C, and F as and of or of fan and K of literals. AC0 is a generalization of that, where you allow sort of arbitrary constant depth. Like you'd have an or of n of ors, or of n of or of n, and stuff like that. Okay, so just imagine having a constant number of layers here, but again with and, or, and not gates. Okay, so we have the literals here on the bottom, variables and negations. Okay, so Russell, Mohan, and William Matthews showed that AC0 SAT can in fact be solved faster. Okay, as the depth increases, so as your constant depth increases, your savings gets worse and worse. Okay, but you still get some kind of savings over to the end. So you think of dividing the exhaustive search by 2 to this amount. It's actually quite a lot. If S is something like polynomial, this is like n over polylog n. So it's a pretty substantial improvement. Okay, but it's not as good as what you get for, say, depth 2, CNF SAT. Okay. All right. So, so there are even more expressive circuit classes one can look at. A very popular basis that people look at for constant depth circuits is and, or, not, and a funny mod m gate. So just think of m as being some fixed integer. It's at least 2. And like, for example, mod 6, it takes its inputs and just outputs 1 if only if the sum is divisible by 6. Okay? Essentially, this class arose from the fact that mod 2 cannot be computed in constant depth with and, or, and not. Okay? This is results proved by first Sachs and Sipser and Aitai. So people thought, well, what if you just add that function in for free into the basis? Well, then you can definitely compute mod 2 with one gate. What else can you do? Okay, so just throwing in this divisibility check. So it will look something like this. So again, constant number of layers, but with mod 6s, ors, and ands. Okay? And so something I proved a while back is that actually there's a faster SAT algorithm for this class, which is interesting because there were essentially no non-trivial lower bounds known for this class, yet you can solve the SAT problem faster. So essentially what this is saying is that, so you fix a depth D and fix one of these modulus M. Okay, now I'll give you a circuit over mod M gates of that depth, and let's say it has sub-exponential size. Okay, so you think of this maybe as like quasi-polynomial in N if you don't like little of ones in your double exponent. Okay, quasi-polynomial N, say. So then you can solve ACC SAT in 2 to the n minus n to the e time. Where this e is less than 1, depends on this depth in modulus. Okay? But no matter what the depth in D is, D and mod M are, if they're constants, then you get some, you divide brute force search by 2 to the n to the e. Okay? For some e. Okay? All right, so.
Can you have several different m's?
You can. So having several different m's is equivalent to taking the product of those m's, having a single type of gate with the product of those m's. So, for example, it's known that if m is a prime or a prime power, then there are very strong lower bounds known. Namely, for computing like say if it were mod p to the k for some prime p, take another prime, a different prime q, you can't compute mod q. Okay, but if I give you let's say mod 3 and mod 2 in your basis, then that's equivalent to having mod 6. Actually, it's not too hard to see. Just a little algebra. But then the lower bound techniques known for doing this just fail miserably. Namely because the lower bound techniques that did this used which I will talk about in a few moments, use the fact that if you have mod p there, then you can take any such circuit and represent it in some approximate sense by a low-degree polynomial over a field of characteristic p. Okay? There's no field of characteristic 6, and this makes the techniques break down for mod 6. Okay? Any more questions at this point? All right, so I will give you an overview of how this SAT algorithm goes because it's quite different from the way you would normally solve the KSAT problem like that. So it takes 2 ingredients. One is complexity theoretic and one is entirely algorithmic. The first is a known representation of ACC. It was known since the early 90s. So it basically said every Boolean function with an ACC circuit of size S, you can express it in a very nice form. You can express it as a composition of 2 simple functions, g of h, where h is a multilinear polynomial with k monomials. It means it doesn't have squares in it. Okay, it has some number k monomials, where k is a quasi-polynomial in S. Okay, so you think of S as being maybe polynomial. This is quasi-polynomial. Okay, so it doesn't have too many monomials. It doesn't have 2 to the n monomials, for example. And as I give you different 0, 1 assignments to this polynomial, it takes on a value between 0 and k. Right?
So the real numbers, or?
Let's say it's over the integers. Okay. Even its coefficients are 0 and 1. Well, if I do that, then if I tell you that, then this condition just follows. But yeah, you can make its coefficients just 0 and 1. But yeah, it's evaluated over the integers. Well, you could even evaluate it mod k plus 1, but okay. So you take that, and then so you have this multilinear polynomial with the smaller monomials, okay? And then you have a filter function, like g, which basically takes something from this larger domain and maps it down to 0, 1. Okay? You can write that as, it can just be arbitrary, and you can write that as a lookup table. What they proved was much stronger than this, but this is the only thing we need. Okay? What they proved was actually much stronger, that in fact this polynomial could have low degree, polylog s degree, and that you can in fact pick a specific function for the g's, but we don't need any of that for the algorithm. Okay. All right, so that's the complexity theoretic part, and the algorithmic part is a fast Fourier transform for multilinear polynomials. So given a multilinear polynomial h and its coefficient representation, so I'd give you the value of all its coefficients for all the 2 to the n possible monomials. There are no squares, so there's 2 to the n possible monomials at most. Then its value, h of x, can be computed over all points in the Boolean hypercube, 0, 1 to n, and 2 to the n times poly n time. Okay? So if I give you like a really long polynomial with 2 to the n coefficients, just naively evaluating it over all 2 to the n points would take 2 to the n times 2 to the n time, right? 4 to the n. So somehow you can make this linear in the coefficient representation, like if it happened to have 2 to the n coefficients. Okay? So that's basically the source of the speed up in the SAT algorithm. Sure. Questions? All right. Okay. So I'll talk a little bit about these polynomials representing ACC. I won't be able to go into too much detail about it, but I hope it give you a good idea about it. Okay? Yeah.
Is that constructed? Like, does it give you an algorithm to compute the polynomial? Or?
Yes, it does. Yes. Yes. What's the running time of it? It's a quasi-polynomial in that. Yeah.
Quasi-polynomial in K.
Mm-hmm. We're going to set S. Right, remember S for us was sub-exponential, like 2 to the n to the low of 1. We're going to set we're going to make this, if you put to the n to the low of 1 here, that's still 2 to the n to the low of 1. Right, this is some fixed polynomial in the double exponent that will get absorbed in the low of 1 in the double exponent. Okay? Maybe I'll write that. So if S is to the n to the low of 1, and this is also to the n to the low of 1. Okay, so for any fixed polynomial there. Okay. And this thing can be constructed efficiently. Okay. So how can we represent ACC with these polynomials? Okay. I was just getting out of the way of the TV, so. There's some very special cases. So here's some like really, really simple cases. How do you represent simple functions using these g's of h's? So if you wanted to write the OR function as one of these g's of h's, what do you need? You need like a multilinear polynomial and you need some filter function. So you could just take the sum of the bits as your multilinear polynomial and let your filter function g just be 1 if and only if that sum is greater than 0. Okay? That will represent OR for sure when you take g composed with h. Okay? And you can do and just as well. Just make it so that you only output 1 if your input is n. Okay, so then all these bits have to be 1 to output 1. In general, for any symmetric function, any function which only depends on the number of inputs which are 1, you can do this kind of thing. Okay? But the ACC circuit is a composition of a bunch of these kinds of things. Right? It's got ORs and ANDs and mod m's like all composed together. So what can we do? We have to be a little more sophisticated than this. So a less special case is the following theorem of Razborov and Smolinski. It's a bit of a mouthful, but I'll say it slowly. So for every AC0 circuit, so again, constant depth and or a not circuit with constant order layers, if it has n inputs, size S, and depth D, so D layers, then there's an efficiently sampleable distribution. So there's an algorithm, D, randomized algorithm which takes C as input. It spits out a polynomial for you. This polynomial has lowish degree. So if S were a polynomial in n, and D is constant, this is like polylog degree, over F2, the field of 0, 1, so that the following holds. Okay? You give me a point, I want to evaluate the circuit C at this point X. Okay? Then whenever I run this algorithm D on it once, and draw out a polynomial P, the probability that polynomial P agrees with C is greater than 3 over 4. Okay? So just drawing out a random polynomial, no matter what X I have, to draw a random polynomial, I'll get agreement with probability at least 3/4. Okay? All right, so this is a way of sort of approximately representing a low depth circuit with a very low degree polynomial. Okay? So in fact, we can use a small number S of polynomials. So this sample space here can be made quite small. Okay, that takes an argument, but it can be made quite small, about n to the polylog S number of polynomials in total could possibly be output by this thing. Okay. So the idea is that, well, once we have like an explicit constructible set S of these polynomials, then I can just take the majority value of what they output over all the different polynomials, right? That would certainly tell us what the value of P of X is, because on a random choice, it agrees with probably greater than 3/4. So if I take the majority of everything, then that's definitely going to give me the right answer. Okay? All right, so I can write the majority. So let me just write down like what this is as a circuit. So there's a polynomial here, but it's really a circuit. I mean, it's really a polynomial too. It's just okay. So you can always think of a polynomial over F2 as a big XOR of ands. Right, where each of these ands is just a monomial, and the XOR is the sum over everything. Okay? So what we're wanting to do is, so this is like, say, a random draw from this distribution, and we're going to take the majority over all these capital S polynomials in the sample space of all these different polynomials. Okay? Now this thing will just give us the right answer. No randomness required. We just iterated over all the randomness, in fact, with this small sample space. Okay? So this majority of XOR of ands will give us the right answer. Okay. Okay, so we're not quite there yet, because what we said was that you get this G of H's. But so a key observation here is that this G of H thing can be seen as a circuit too. Okay, so right, this thing is a multilinear polynomial, so we can think of it as a summation over the integers of AND gates, right? And we said it had not too many monomials in it, so it had some number k monomials. Okay, then we had some filter function g, right, which took the sum and then gave us a 0 or 1 value. Okay, well, all that's really doing is just computing a symmetric function of these ands. Okay, so all this is really doing is just giving you, so this is h, and this is something that maps 0, 1 to k, 0, 1. So you can write this whole thing as some symmetric function. So I write that as SYM sim of AND gates. Is it visible?
Not easily.
Not even visible?
Not easily.
Not easily visible. Well, I want to make it easily visible. Is this more visible? Or just, I mean, maybe it's more visible, but now it's more disgusting to look at. So, well, there's a trade-off, I guess.
The color that contrasts most with white.
Yeah, well, that one ran out. Let's see. Okay, fine. Whew, jackpot. I guess no one's been over here today. Okay. Good. Okay, sim of ands, all right? So we have a majority of XOR of ands. We want to make it look like this, okay? And so you can actually write a majority of XORs as a symmetric Boolean function, in fact. This is totally not obvious, or at least not obvious to me, starting with the work of Yao. It actually was very key to Toda's theorem that the polynomial hierarchy is contained in P to the sharp P, and it appears, obviously, in this Beagle-Taruri result about ACC. So there's a way to take a majority of XORs and actually pack the whole thing into one symmetric function. It's pretty remarkable. Okay. But that's one of the idea about how you do this for AC0. And for ACC, well, it gets more complicated, obviously. But and there's like several different steps that go into it. Okay. But is the basic idea clear? Okay. Let's see.
Your capital K so far have been n. Is this now changed? Have I now lied?
What?
The range to which, I can't remember, H maps
Oh,
to K. So in the examples we've seen so far, that has
this is supposed to be a K. Does that help? This K is quasi-polynomial in the circuit size. So let me give a little more detail about this Razborov-Smolinski distribution, because it's not too hard to fit the whole thing on a slide and sort of understand it, but at the same time it's very subtle, and people are still kind of toying with it and working out its consequences. So here's the theorem again. Okay. So I threw in a parity here. That just means I'm allowing mod 2 gates as well. So I allow OR and mod 2 and not. Okay. Again, I have n inputs size S and depth D. And I want to get this efficiently sampled distribution with this property. So for every point X, pick a random polynomial from the distribution. Probability agrees with the original circuit is at least 3/4. Okay. So the proof idea is by induction on the depth D. So in every layer, we're going to get a polynomial of degree about log S. Okay, that's randomly representing the gates at that level. Then we're just going to compose them all. There are D layers of depth, log S degree in each one. When we compose them all, we get log S to the order D degree. So it's the composition of D log S degree polynomials. Okay? So NOT gate is pretty easy to do. Okay, over F2. NOT gate, 1 plus X of I. All right? XOR gate, no sweat either. All right, over mod 2. All right? So the OR gate is a tricky part, and we do it as follows. Okay? So for every X, which is pointing 0, 1 at the end, observe the following. If I take a random vector, 0, 1 vector, and I take its inner product with the inputs x1 through xn, the probability that agrees with the OR is at least a half. Okay? Just a random subset sum principle. Okay? Yeah, so how many people have seen this kind of argument before? Most everybody. Okay. Okay. So, all right. So we want to do this and amplify it. So 1/2 is not enough for us. So we want to have a probability of success which is very large. Let's say 1 minus 1 over poly S. So that way, for a size S circuit, if we take a union bound over all the gates, it'll still work with high probability. So to do that, to get a better trade-off, we do the following. So instead of picking one random vector, we pick k random vectors, okay, where k is some error parameter. So think of this as picking like a k by n random matrix. All right. So for all 0, 1 points, we're going to form the following polynomial. Okay, now this polynomial is of degree k. So we're taking a product over j equals 1 to k of some sums. We're adding 1. Okay? So I claim that the probability this degree k polynomial agrees with OR on a given point is at least 1 minus 1 over 2 to the k. Now let's see what happens. Okay? Suppose the OR of this is 0. Okay, suppose all the bits are 0. All right? So every one of these linear combinations are going to be 0. Right? So I add 1. They're all 1. The product of all these 1s is 1. But I add another 1, so it's 0. Okay? So that happens with probability 1. Okay, so if the OR is 0, if all these bits are 0, then this polynomial always evaluates as 0 over F2. Okay? All right? Now suppose it happens to be 1. Okay? So then each of these has a 1/2 chance of turning out to be 0, right? Because this has a 1/2 chance of agreeing with OR, When I add 1 with it, it has a 1/2 chance of turning out to be 0. So I'm taking a product of k independent things, each of which has a 1/2 chance of being 0. Okay? So I have only 1 over 2 to the k probability of error. Okay? All right, so this is a degree k polynomial simulating or with error at most that. Okay? So what I'm going to do is I'm going to set k to be like 10 log s, for example. Okay, then my error probability in any particular point is at most 1 over a polynomial in s. Okay, so if I union bound over all the s gates, still have great chance of working. Okay, so I have degree order log s polynomials on each of these d layers. When I compose them all together to get a single polynomial, is going to have this degree, okay, just by simple composition of polynomials. Okay. Any questions about it?
So the bound is actually log s to the d.
Yeah. In fact, you can get d minus 1 if you really want. But okay. Yeah. Even as one slide proof, the bound is log s to the d. Yeah. Yeah. I mean, yeah. Try to find the shortest proof you can of this statement, and we'll compare at the end. Okay. If you get bored, or if you sleep. Okay. All right. So that's the polynomials. So now I want to talk about the algorithmic part of the algorithm. Okay. So this is this fast multi-point evaluation. Okay. So I have some multilinear polynomial in variables. Okay. I give you its coefficient vector. Then its value can be computed in all points in the Boolean hypercube and to the n times poly n time. Okay. This is actually can be seen as a really simple divide and conquer. Okay. Given any multilinear polynomial, so it has no squares at all, you can always write it as x1 times some polynomial in the last n minus 1 variables plus some other polynomial in the last n minus 1 variables. Just separate the monomials that have x1 from those who don't. Okay? Everything's commutative, no problem. All right? So, okay, we want a table T that contains the value of h in all 2 to the n points. We can just recurse on h1 and h2. Okay? That's the whole algorithm. Okay? So if n is equal to 1, if you've got one variable, then okay, you just evaluate the one variable twice. Okay, 0 and 1, and you turn that table. Otherwise, you recursively compute table T1 for the n minus 1 variable polynomial h1. It gives you 2 to the n minus 1 linked table. Similarly for h2. Okay, so then you say, okay, well, what do I want back? Well, I want to say, just give me a table of 2 to the n entries. So I'm going to concatenate T2, the whole table for T2, with the component-wise sum of the table T1 plus T2. Okay? And so when x1 is 0, this term cancels and h equals h2. So that's x1 equals 0 part. When x1 equals 1, it's just h1 plus h2. So the component-wise sum is capturing that. Okay? So I just returned this concatenated table. No big deal. All right? That's the algorithm. That's it. Okay? So the running time has this occurrence. Okay, I want a table of size 2 to the n. I do 2 recursive calls to get 2 to the n minus 1. And I do some extra stuff to like sort the monomials, say, component-wise add 2 to the n times poly n, most. And so this recurrence just solves the 2 to the n times poly n as well, for a slightly bigger poly. Right? Okay, so using this, you can compute the g of h, for any g looks like this, 0, 1 to the k to 0, 1. And any multilinear polynomial h on all possible assignments in only 2 to the n times poly n time. Okay? So this algorithm definitely tells you how to get all the values of h, all the outputs of h. Then to get the outputs of g, you can just do some simple sorting to do that. Okay? All right, so using this, you can evaluate one of these sim of an's or g of h's on all possible points very efficiently, even if this thing happens to be big, like 2 to the n to the O of 1 size. Okay? In fact, the way it's written here, this thing could just be even 2 to the n size. That would work. Okay? All right. All right. So now I'll present the SAT algorithm. Okay. So the theorem is for all depths d and moduli m, there's an epsilon, so the ACC SAT so ACC M just means it's got mod m gates in it, with depth d and inputs and 2 to the n of the epsilon size can be solved in 2 to the n minus omega n of the epsilon time. Okay? All right. So this definitely gives us the theorem if it has sub-exponential size. Okay? For 2 to the n to the little of 1. All right? So we start with a circuit C. It's got 2 to the n of the epsilon size and n inputs. All right? So the first thing we do, it's a little strange when you first see it, but eventually it just becomes natural, is to do a mild brute force inside the circuit. So let the circuit itself simulate a mild brute force. So what we do is, for example, take the first n to the epsilon inputs to the circuit, try all possible to the n to the epsilon values for it, okay, and take the OR of all the circuits you get from plugging in these different into the epsilon bit assignments. Okay? So I'm just taking the first n to the epsilon inputs, trying all possible assignments to them. For each one I get a different subcircuit. Okay? Now I just take the OR of all that. Okay? So I've blown up the size of the circuit by some amount, some quadratic amount, but the number of inputs has gone down. Okay? So it's sort of a size input trade-off. Okay? So there's sort of two important things to note here. If C is an ACC circuit of depth D, then this, say, C prime is the ACC circuit of depth D plus 1. Okay, just added an extra OR here. Okay. The second thing is this C is satisfiable if and only if this C prime is satisfiable. Okay. So if this has a satisfying assignment, there's some way to set the n to epsilon and make this thing print 1 on something here. There's some subcircuit simulating exactly that, and it will print 1 here on the OR gate. Okay. So we preserve satisfiability by doing this trick. So then we run this Beagle and Teruri, this G of H decomposition on this circuit. Okay. So we get a G of H's. And so what this does is it blows this up by a quasi-polynomial. Okay. But quasi-polynomial in this translates to 2 to the n of the order epsilon up here. See? So if you've got, so again, as I erase it, okay, it's 2 to the n of 1. If S is 2. Okay. All right. So we got this G of H's here, which we can also write as a sim of ands thing. And now we just use this FFT algorithm that we had, okay, on this thing. But the key point is that this has a smaller number of inputs than before. So when we evaluate this thing on all possible inputs, we actually have something running faster than 2 to the n. Okay? So we can evaluate this object on all of its possible inputs in polynomial amortized time per assignment. So if this has got k inputs, we can get 2 to the k times poly n. And so what we end up doing is getting an evaluation that runs in 2 to the n minus n to the epsilon times poly n. Okay? And so once we've evaluated this G of H on all of its possible assignments, right, we just need to check if it ever printed 1. Or if it ever prints 1, we know it's satisfiable. If it always prints 0, right, then this thing is unsatisfiable, so this thing is unsatisfiable, and therefore this thing is unsatisfiable. Okay? So we're just checking if this thing ever prints 1. Okay? So this is a very different paradigm from backtracking, local search, the other things Tora mentioned yesterday. But it's still giving you something for some circuit class that we had no idea what to do. We had some complexity theoretic way of expressing it with multilinear polynomials, but we didn't know what to do with it. And SAT algorithm gives you a way to reason about it. All right. So for example, starting from ACC, you can take more expressive circuit classes like formula SAT. So for De Morgan formula SAT, where you got formulas over and or not, and each gate is finite at most 2. It's known that you can get faster SAT algorithms for formula SAT, but only for formulas of size up to roughly n cubed, which is interesting because this is exactly the strongest lower bound size that we know for De Morgan formulas as well. And this is not really a coincidence. Okay, there is a good explanation for that. Like basically the same kinds of ideas which get you limitations on formulas up to cubic size also allow you to get really fast branching algorithms for formulas up to that size. Okay. And for formulas over, let's say, AND or not an XOR with fan N2, you can also get a formula SAT algorithm faster. Again, up to this not cubic, but quadratic size. And that's, again, exactly the place where the techniques, the lower bound techniques, no longer apply. We don't know how to get super quadratic lower bounds there. And for, let's say, generic circuit SAT over AND or not with fan N2, I think a big open problem is, can we improve over exhaustive search? Can we improve over 2 to the n times s time? Can we? Oops, I think I accidentally just ended the presentation. Oh, okay. Yeah. So, can we just do anything better than exhaustive search here? I don't really know. Okay.
Strange number 1.99 or 2.99. From where it comes?
What's that?
Some cubic number 2.99. From where it comes? Or
where does it come from?
1.01 or
what's that?
Why not 3.01?
Oh. So you can put like 3 minus like little o of 1 roughly here. I mean, like, yeah. I mean, it's essentially 3, and this is essentially 2. Yeah, that's all I wanted to convey. Yeah. Oh, I thought you wanted like me to explain the lower bound, but that's another time. Okay. Yeah, I can do that too. All right. So, okay. So that's enough about circuit SAT. Okay. So I want to speak briefly about a problem that Russell mentioned, and just sort of talk about in a survey style. So, but this is not just for like generic circuits, as Russell's been doing, but like different circuit classes, you can talk about the same kind of thing. So if you let fancy C be some class of Boolean circuits, define some circuit approximation probability problem for it, which is given a circuit K. We want to output a value V so that it closely approximates the probability that on a random assignment the circuit accepts. Okay? We're just approximating the probability the circuit accepts. Okay? And this 1 over 10, it's just some arbitrary thing. You can, as usual in these randomized things, you can modify this constant. Okay? So we want to solve this problem deterministically. Okay? Solving it with randomness is very easy. Just randomly sample inputs and see what happens. So, as Russell's been mentioning, it's related to pseudorandom generators and de-randomization, very intimately linked. So I won't say much more about that. I do want to talk about like the progress that has been made on restricted circuit classes for this. Okay? And it's interesting to note that the progress we made here, so the running time algorithms for here are much better than the algorithms for SAT. Okay? And there's a reason for this. And we actually believe everything on this slide is solvable in polynomial time. Okay? We believe P equals BBP, so this problem should be solvable in polynomial time, deterministically. So everything here should be polynomial time, but this is what the progress we have so far. Okay? All right, so we can't say that about circuit SAT, I guess. All right? So for AC0 circuits, if you want to approximate the probability the thing accepts, you can do it in time quasi-polynomial in the circuit size. Okay? But you again have some sort of exponential factor in the depth, so, I mean, it's worth comparing these two things. So I had like log 4s for this, and for SAT, I had something like this. Okay, so this is for SAT, and this is for CAP for ACC. Right? So quasi-polynomial versus slightly better than 2 to the n. Okay. So for C and F, the CAP problem is in almost polynomial time. So the closest problem I know to being polynomial that isn't actually polynomial. Yeah. Maybe I'm not. Do you know something with a lower exponent than this? Is it? Okay. Yeah. So it's almost certainly in polynomial time, and probably doable. I don't know. What do you think? Is it doable? Okay. Anyway, so into the log n time. Okay, if you've got say poly n clauses. Okay, so this is stark contrast from like us with CNF SAT. We're just trying to be 2 to the n. We're just trying to get 1.9 to the n. Okay. All right.
So poly n clauses means the number of clauses is poly n.
Yes. Yes, a poly n number of clauses. Yeah. Yeah. Now, as we increase the complexity of the circuit, this is the bounds we know are worse and worse. So for De Morgan formula cap, so this is n or not, no XORs, you can get into the 2 to the n to the e time. So this is e being some e less than 1 for formulas of size up to cubic. Okay. Recall for SAT we were taking 2 to the n minus n to the e. Okay. So this is still very nice. Getting that for SAT would be amazing. This is what we get for approximating the probability. Okay. And then for general formula cap, again, we can do this right up to the best circuit lower bounds. And these all use different techniques from lower bounds. Okay. All right. So yeah, again, we think that all these are solvable deterministically in polynomial time. Okay. And solving them faster does give us some insight into the function being computed by the circuit. Okay. It's some circuit analysis problem. Yeah.
This might be a stupid question, but this the probability of x.
Yes.
What's the probability? What is the x sample with different probabilities, or is it just like the frequency?
Oh, it's just uniform.
Okay.
Just flip each bit of the input probably half.
Okay, so it's just like the frequency of.
Yeah. It's no different from like computing the number or approximating the number, the fraction. It's in a constant. Yeah. Okay. So I want to talk a little bit about other circuit analysis problems, not just ones that take circuits as input. So circuit analysis problems can also analyze functions directly. So the canonical example of this is the minimum circuit size problem, which has been studied for a very long time. So here the input is a 2 to the n bit truth table of a Boolean function. So I'll give you like the value of the function in all possible inputs, and I give you some parameter s. And what I want to know is the minimum size of a circuit computing this function at most s. Okay, so I give you the function, and now I want to know something about its circuit complexity. Is the minimum size at most s? Okay, so this is a decision version of it. You could imagine taking the truth table and just trying to compute what is the circuit complexity of it. Okay, over n or not, n into. Okay, so it's important to note that this problem actually is an NP. Okay, because I give you the whole truth table, the input is of length 2 to the n. So, the maximum size of the circuit can be, of the circuit complexity, is, at most about 2 to the n over n, in fact. And so you could just guess that circuit, and just evaluate all possible inputs and check. But the input is of length 2 to the n, so this is poly 2 to the n, no problem. Okay, so this is an NP problem. Okay? And it's widely conjectured this problem is not contained in polynomial time. If it were in polynomial time, we could break any pseudorandom function candidate, for example. So if any circuit that's trying to pretend it's a random function would not be, using our powerful polynomial time algorithm. We could just compute the circuit complexity of what it's giving us, supposedly pseudorandom bits. Okay? Now, it's known, in terms of hardness, it is known that if I want to find the minimum size of a DNF computing this function, that is NP-complete. Okay, somehow, we understand DNF really well compared to circuit complexity in general. This uses lower bounds on DNF actually to get. So a big open problem is whether this problem is actually NP-complete. And recently, with my student Cody Murray, we've made some progress on this question. We've shown that if it is NP-complete, then it would imply it has to require techniques that are just, not like any other polynomial time reduction we've ever seen. So what we show is that if MCSP is NP-complete under poly time reductions, then X was different from ZPP. So we get some result of the form that Russell was lamenting about we don't know how to prove. Okay? Just from a polynomial time reduction showing this thing is NP hard. We would have a separation. We would be able to show randomness is not super powerful. We still don't know. So if it is NP-complete, it would have to have some consequence no polynomial time reduction I've ever seen could do. So it has to be radically weird. And we show that for more restricted reductions in polynomial time, you can actually rule out that it just simply is not NP-complete under more restricted reductions.
I'm sorry, what reductions?
Okay, I can be more specific. Polylog time projections. So where each bit of the reduction can be computed in polylogarithmic time. Yeah, we can prove that it's simply not NP-complete under these reductions. Okay, I'm running low on time, but I think I'm towards the end. Okay, so open problem is to find any improvement over exhaustive search for this problem. Just anything better than just trying all possible circuits of size S and seeing what happens. Let's see. Okay, so I'm almost done. So,
Is this a candidate for a problem not known to be NP, not NP hard, and not allowing A to be?
Oh, is it a good candidate for a problem that's not known to be NP hard, but could require whatever, exhaustive search? Yeah, I think it's a really good candidate for a problem like that. But it probably is NP hard. It's just going to require, understanding the power of randomness first. That's my opinion. I mean, you could think of it different ways. You could say, polynomial time reduction shouldn't imply that, so it's unlikely. I think it just means that we're going to have to learn a lot more about circuits and randomness before we can. Yeah.
Well, why do you think it's NP hard rather than just hard? And
could be just hard. It could just be simply not solvable in polynomial time. But not expressive enough to be NP hard. Yeah. That could be true too.
So if it's not NP complete, there are no known consequences. As far as
I don't think so. I don't think I know anything off the top of my head. No.
okay. So.
I mean, at the same time, I wouldn't consider that unlikely. So.
Right.
Yeah. But it's just weird. Yeah, it's weird that it implies it. Did you have a question?
The polynomial reductions you were mentioning, are they like it's deterministic?
Yeah, they're deterministic mini-1 reductions. Yeah.
Oh, but the first result, the
This thing?
yeah. Is that what about reductions like non-uniform?
Oh, non-uniform reductions. That's a very interesting question. Yeah, we don't know results for that. But if we look at polylog time projections, even randomized polylog time projections, even like algorithms which read like up to like a cube root of n bits of input and then output a bit, even if they're randomized, we can show they don't exist. So I guess this is basically saying that any reduction, even from the parity problem to MCSP, you can show such a reduction. So like any reduction showing a hardness of MCSP for practically anything is going to have to be very non-local. I mean, which sort of makes sense. I mean, because you're supposed to be printing something that's hard circuit complexity. If it were local, then it should have a maybe smaller representation. Okay. Well, I'm clicking. I see things happening, but. Okay. So a couple more things I wanted to mention was that there's been a lot of results about showing the power of circuit minimization. So showing that it can do things that we don't think can be solved. For example, factoring, integer factorization, can be done in randomized polynomial time with an oracle for circuit min. The discrete logarithm problem, similarly, can be solved in be slightly different version of randomized time. And even graph isomorphism can be solved using an oracle for circuit min. So these are some pretty remarkable results. Eric Allender is the A on all these things, been leading the charge on them. So some open problems about this is I would like to find some interesting problems in P with an oracle for MCSP, because right here these are sort of randomized Turing reductions in a sense, right? Like showing that with randomness and being able to compute circuit complexity, you can do all kinds of interesting things. What if you don't have randomness at all? Okay. So here's another thing. So if I give you the truth table of a circuit, I want to know its circuit complexity. I don't know how to produce a minimum size circuit from that. I can only tell you whether or not the truth table I'm given is easy or hard. So can you get some sort of self-reducibility? Can you produce a circuit given a truth table with an oracle for the circuit? Okay. Another question is, how hard is this thing for AC0 circuits? Okay. So we know it's NP hard for DNS. Is it sort of, but we know that, like, okay, we have exponential lower bounds on DNS. We don't have like truly exponential lower bounds on AC0, so maybe we can prove some kind of hardness for quasi NP, non-deterministic quasi polynomial. Okay. So all these different algorithms for circuits is just one tiny part of this area of exact algorithms for NP hard problems, which we'll see a lot about this semester. Lots of cool open problems. A few of them mentioned here. And here's the outlines of the rest of the lectures again. Circuit complexity, connections, and Aknown ACC. Okay. Sorry for taking up so much time. Yeah.
Do you know anything about printing not the minimum size circuit, but printing a reasonable size circuit?
Oh, so this is sort of like the compression problem, yeah, that Valentin's been looking at.
With P to the MCSP, though.
Oh, in P to the MCSP, I haven't thought about that problem at all. Yeah, so trying to print like some circuit that's not like a minimum size circuit, but just like approximately.
Minimum size circuit.
I haven't thought about this problem at all. Sounds like a good problem. Yeah.
Another question?
I have an organizational question. Is there still somebody who feels responsible for ensuring that all the open questions from the talks will eventually find their way to the open problem board?
Yes,
Because that would be nice.
It was an open problem coordinator.
Yeah, exactly. And is the open problem coordinator still?
Coordinating? Yeah, he's coordinating, I think.
it will might probably happen like early next week, but it will happen at some point.
Brilliant. Thanks a lot.
So the meta problem that you're considering here is the circuit SAT, circuit minimization.
Yeah.
What are the meta problems on circuit that also give you interesting concepts like?
So in a longer version of this talk, so not only talk more about CAP, but also this question of compression. So you're given a truth table and of some function, and you're promised it has a circuit. And when it has a circuit of reasonably small size, you can output some non-trivial circuit for it, right? Like something like weaker than MCSP. Yeah. Yeah. So obviously that's useful. I mean, in terms of other problems, I mean, not really. This is sort of the constellation of problems that people don't. So, but that's for algebraic complexity. I mean, that's a totally different talk. And well, actually, Russell's giving that talk, isn't he? Okay.
Equivalence testing or
equivalence testing. Oh, checking whether equivalent. Yeah, but this is more or less SAT. I mean, with an extra gate at the top. Okay. From SAT, you can get a lot. Yeah. Thanks.